Now, it's time for a brief exploration of inter-AS routing, which is when policies become important in control plane decision-making. BGP, defined in RFC 4271, which stands for Border Gateway Protocol, is the de facto interdomain routing protocol. It is called the glue that holds the Internet together. BGP has two components: external BGP, eBGP, and internal BGP, or IBGP. Remember the responsibilities of the inter-AS routing we discussed. eBGP is responsible for obtaining subnet reachability from neighboring routers. IBGP propagates that reachability information to the routers within one AS. In other words, an AS tells the rest of the world that it exists using eBGP. Propagation of that information to each router within ASs is done by IBGP. BGP runs over TCP. The routers within each AS have logical IBGP connections. Note that in IBGP, these are TCP connections and might not correspond to physical links. The gateway routers run both eBGP and IBGP. They have eBGP connections with the gateway routers from other ASs, and IBGP connections with routers within their own AS. Two BGP routers that have TCP connections are called peers. eBGP peers exchange advertisement of paths to different destination networks. BGP is a path vector protocol, as it works with building vectors or lists of ASs that need to be crossed in order to reach a certain destination in the network. For example, in this figure, AS3 gateway router 3A advertises path AS3X to AS2 gateway router 2C. In this way, AS3 promises to AS2 it will forward datagrams towards X. This is a path vector towards X, containing AS3. Means in order to reach X, packets from AS2 can go through AS3. The goal of inter-AS routing is to find paths to reach specific prefixes in the network. BGP advertises those prefixes with a set of attributes to maintain them as routes. Two important attributes are AS path and next hop. AS path is the list of ASs through which prefix advertisement has passed, the path vector. Next hop indicates the specific internal AS route to next hop AS. There are many other attributes: local preference, locally preferred, AS path length, that can help decide the next hop to an AS or an external destination when we are within an AS. A natural question at this point is, well, where the policies are applied. Gateway receiving route advertisement uses import policy to accept or decline paths. That policy can have a form similar to this statement: never accept a route through a certain AS like Y. AS policy also determines whether to advertise paths to other neighboring ASs. For example, ASX might not want to route packets of ASY, in which case it does not advertise routes to it. Let's go through a simple BGP example together. In the shown network, let's assume AS2 router 2C receives path advertisement AS3X from AS3 router 3A using eBGP. Based on AS2 policy, AS2 router 2C accepts path AS3X and propagates it to all AS2 routers using IBGP. Based on AS2 policy, AS2 router 2A advertises path AS2 AS3X to AS1 router 1C using eBGP. Similarly, based on AS1 policy, AS1 router 1C could accept path AS2 AS3X and propagate it to all AS1 routers using IBGP. at which point the whole network could have the information of who to reach X through using the vector they have been advertised to. However, a gateway router may learn about multiple paths to destination. For example, AS1 gateway router 1C, which had previously learned the path AS2 AS3X from 2A, now learns the path AS3X from 3A. Based on its policy, AS1 gateway router 1C chooses path AS3X and advertises path within AS1 via IBGP. BGP messages are exchanged between peering BGP routers. The peering happens over TCP connections. BGP messages to open and maintain these peering connections include open, update, keep alive, and notification messages.